Welcome to this channel. Make sure to subscribe. So today we'll be looking at real analysis for higher level courses. Real analysis. And the first thing we want to look at before we proceed is open and closed interval. So open and closed interval are very important. We need to know the differences because we will make use of ordered pairs in real analysis. And ordered pairs has to do with this. So our closed interval now are compact sets. That is, they include all their limit points, and they can be represented as bounded linear regions. And their order of endpoints doesn't have to matter because all the points are included. What is this trying to say? Just imagine yourself moving on a straight line. Take for example a 1 meter rule. In a 1 meter rule, you have point 1, 2, 3 to 100. So as you're moving from point 1 to point 100, you are actually going to pass through 1 to 100 and get to 100. If you interchange coming back, you are coming from 100 to 1. This does not affect the rule of closed interval. But open interval are open sets. That is, they exclude their boundary points and often arise in situations like continuity or differentiability of function domains. Now, for this open interval, take for example, you are asked to move on a meter rule, but you have to move in between 1 and 100. That is, if we represent this mathematically, we'll be having x is less than 1. That is, x is greater than 1, less than 100. X is greater than 1, less than 100. So that is what this means. You must not start from point 1. You start from the next point after 1. And then you must not attain the 100 point. So that is just the difference between the open interval and the closed interval. So the next one we want to look at now is our Cartesian product of sets. And in this Cartesian product, we make use of ordered pairs, that is open interval brackets. So now for our Cartesian product is represented as, we use letters like x cross y. So the Cartesian product x cross y of x and y is actually a set of all ordered pairs. Like I said, you're making use of the open interval brackets. So it is a set of all ordered pairs x, y, such that our x is in set x and our y is in set y. So this creates a new ordered pair x, y, that is represented there. Why? Because x is coming first before y. Assuming the Cartesian product is y cross x, it will be y, x. So the order is very important in the Cartesian product and in the open interval. So since you're making use of open interval, you have to be very careful about the order. So x comes before y in this Cartesian product, so we have x, y. So in this instance, our x, y is not the same as y, x. Y, x will only hold if the Cartesian product is y cross x. So now we can be able to define relations. It is where we begin, where the focus of real analysis starts from. Relations. So with relations now, relations have to do with the Cartesian product. And the relation is expressed, is the subset, is assessed as a subset of our Cartesian product. And then to represent a relation between two things like x and y, two sets and x and y, we represent it as x, big R, y. That's how to represent it. So a relation is a subset of a Cartesian product, like I said. Remember, our Cartesian product is x cross y. It's a subset. Thus, our R, which is our relation, in such a way that we have x, y, not open interval, but ordered pairs. So that x, y is in our R, is in our relation, is a subset of a Cartesian product. So it is represented as x relation y, xr, big R, y. So let's look at domain and range of a relation. So now this domain and range of a relation takes us to mapping. Here we have a domain, we have a range. So a range is just a set of images that elements in a domain are mapped onto. The images in our codomain, that is what we refer to as range. So our domain of a relation is the set x such that x, y in brackets is in R. Is in our real field. It is also our relation. And the range of our relation is a set y such that x comma y is in R for some x, while the first one is for some y. And our R inverse is just negating our relation. So wherever you see x comma y, change to y comma x. So that is the inverse of the relation, R raised to minus. So let's move forward. Let's go into reflexive, symmetric, and transitive relations. So when we talk about a relation to be reflexive, a relation is reflexive, it is mapped onto itself. Now what do we mean by being mapped onto itself? Just for an example, when you look at the mirror, what do you see? You see an image of yourself. You literally see yourself. So it's like you are mapped onto yourself by the mirror. So the mirror is a relation in this instance. Why you are x and your image is y. So we say it is reflexive. So it is reflexive in this instance, where x, relation x, or x in a set s is set to be reflexive. So let's look at the other situation where our relation will be symmetric. When we talk about symmetry now, we try to say that, okay, if x is related to y, this means that y is related to x. For all x and y, which is in our big set x. An example for this is just small numbers. For this instance, we can say we know that the number 1 is less than 2. And this also means that 2 is greater than 1. So in this instance, we can say the relationship between 1 and 2 is what is symmetric. It is symmetric. We can also have this in the form of the ordered pairs, where we have 1, 2 is symmetrical to 2, 1. So that will be the standard representation with ordered pairs. So now a relation is also said to be transitive in a situation where if x is related to y and y is related to z, that means that x is related to z. So for an example now, we can take a situation where 2 is less than 3, 3 is less than 4. Then this actually tells us that 2 is also less than 4. So our less than now is the relation. The term is less than is the relation between 2, 3, and 4. So it is said to be transitive. If we reset it in a set of ordered pairs, this will be 2, 3 in ordered pairs, then another one 3, 4. So we'll say this is transitive. But in real life situations, when it comes to humans, when it comes to our daily life, the transitive, reflexive, symmetric laws of relations may not hold. Take for example, when it comes to relationships between people. Take for an example, you liking somebody does not mean the person likes you. Yes. Or if a guy likes a girl, does not mean the girl likes another guy. So in terms of this real life situation, the relation may not hold for any. It may not hold for transitive, it may not hold for reflexive, it may not hold for symmetric. Because it doesn't have to be like that in a set of humans. So let's proceed. Forward. So next, let's look into in our next chapter. Let's take a break small. In the next chapter, we'll be looking at equivalent classes. Equivalent classes, probably partition of a set. We'll also look at several other things that has to do with relations and functions. So I think that will be all for this chapter. The next chapter is there. Let's take a break. We'll be right back at this moment. And don't forget to subscribe to our YouTube channel so you can always be updated on our new episodes, on our new videos to help you in the long run.